Welcome everyone to today's session. Today is, I believe, March 12th? Yes. March 12th, Wednesday. The paper topic is ReasonFlux, Hierarchical LLM Reasoning via Scaling Thought Templates. Now, this title needs quite a bit of unpacking, and let me do so. It is from authors from Princeton University and Peking University. And I felt that this was really a very interesting piece of work. It is these days, reasoning models that have been trained through reinforcement learning have been getting a lot of attention. DeepSeek R1 has made this topic or this area of research front and center. To give you a backdrop, we realized that DeepSeek R1 was trained, taking a pre-trained model, which was DeepSeek V3, but making it into a reasoning model through reinforcement learning could be done with an equivalent of $5 or $6 million, $5.6 million compute budget, which was astonishingly small, considering that it could achieve state-of-the-art performance at reasoning comparable to other frontier models like O1, OpenAI's O1 and so forth. So subsequent to that, a lot of research has happened that has validated that indeed reinforcement learning is an amazing idea, and that you could you can take a pre-trained model, a foundational model, and train it into reasoning using reinforcement learning with a fairly small model. I suppose at one point, UC Berkeley, someone trained a tiny LLM into a reasoning model with a $30 budget. So by now, we have all internalized two facts. First is that it is a great idea to use reinforcement learning for creating reasoning models. It's a frontier. And secondly, that it could be done at a far lower price, a compute budget than we had previously thought. So with that as a backdrop, I will now speak about this paper. What this paper, the core of this paper is quite interesting. It says that if you look at the way DeepSeek R1 was trained, for example, or the way people train reasoning models, they use chain of thought, step-by-step thinking as the training. You'd use reinforcement learning to force a machine into a long chain of thought to solve a problem. The problem with that approach is it doesn't always work, and you don't know how long it has to think. In this paper, they address that in a very, very interesting manner. They create a library, just to give you a gist of it. You have a library of almost like Lego blocks. You have a library of templates that each template solves one specific, it's like a thought template that if you see this pattern, then this is the way you would go about solving it. And they create a really good library of around 500 high-level thought templates. And then, roughly speaking, what they do is that they use given an input problem, they answer it in the following phases. First, they say, let's plan it out. Let's break it up into sub-problems. What are the steps needed to solve this problem? Once that has been decided, then each step is mapped to, from the template library, to an appropriate template that is most appropriate as a demonstration example to solving that step. And therefore, that step and that demonstration example of sorts, that thought template as they call it, is given to an LLM to say, it's almost like in-context learning, using this now solve this step. And then that particular step gets solved, and it leads to some result. And the very interesting thing is that it might produce some surprises or some things. It may uncover some subtleties, in which case this ReasonFlux framework will re-strategize and add more steps, or sort of dynamically at inference time adapt its process. So there's a lot of very interesting things going on in this paper, and I will go into it iteratively. So this thing has a mix of supervised fine-tuning as well as reinforcement learning, as well as inference time template scaling. So many good ideas come. And in some sense, it has the flavor of RAG, because you're mapping each sub-step, a sub-problem, to a template that you retrieve from a template library. So it sort of has a built-in flavor of RAG. So with that general background, the key in this is that when you try to reason about a complex problem, there's so many different approaches you can take. The combinatorial, there's a combinatorial explosion of possibilities. And so there have been, like, if you remember, a chain of thought evolved into a tree of thought, which said that at every step, don't just think of the next step, think of a group of next steps, many next steps, and from them, there, pick up the most promising ones. Then a further evolution of the tree of thought was the graph of thought. The graph of thought said, okay, don't just have a tree-like structure, allow for a more like a dependency graphs between some sub-steps that have been solved. And you can go in cycles and so on and so forth. So it became a graph of thought, which was quite an evolution. And this takes it much further, because in each of them, the big constraint is that there's a compute budget. The more you do at each node, the next step, number of next steps you consider, and so on and so forth, your inference time compute cost goes up. And so those approaches don't fare so well with respect to the exploration versus exploitation strategy. You can't go on exploring too many possibilities. But what this paper's key idea is that you can have much better exploitation strategy simply by saying there is a finite library, a small library of just 500 templates, which for certain domains like mathematical reasoning are enough to solve a majority of the problems. Majority of tough problems can be solved. And we will see it as we make progress with this paper. So with that background, let us now read this paper. And as usual, I'll be writing and highlighting in this paper. To expedite this paper reading, this time I have pre-highlighted some of the statements, because that was one of the feedback somebody gave me. Why don't you come with the important statements already highlighted? So there we are. I'll just read the abstract and the key sentences in the abstract. We present that hierarchical LLM reasoning via scaling thought templates can effectively optimize the reasoning search space and outperform the mathematical reasoning capabilities of powerful LLMs like OpenAI's O1 Preview and DeepSeek V3. So one thing to mention throughout this paper, when it comes to DeepSeek, the comparison is only to DeepSeek V3. Only at the very end, at one point, it mentions DeepSeek R1. And when it does mention, it just mentions the fact that the reasoning traces that ReasonFlux, this paper does, are far more explanatory than what DeepSeek R1 would do. But for the rest of the paper and much of the analysis and comparisons, it is the DeepSeek V3, the base model that, on which R1 was based. That is the basis of comparison. Just something to know. So from that, we can deduce that this work was done, much of the work was done prior to the release of R1. So let's continue from there. So the important words are the hierarchical LLM reasoning. And what does hierarchical LLM reasoning mean? We'll see. And scaling thought templates. What that means is that As you solve the problem and the problem gets more and more complex, it will automatically use more and more of those thought templates or Lego blocks. So it scales very naturally. The complexity of the problem determines how many Lego blocks you will bring to solving this problem, which is interesting because if you remember, a lot of the reasoning models these days, they start with a finite budget. They pre-allocate a budget, that this is the inference time compute budget we keep to solve this problem. Sometimes that budget is too much, sometimes that budget is too little. And so one of the nice things is that it is, in this particular case, it assesses the complexity of the problem and in a very natural way, dynamically scales forward. So there are a lot of very good things in this paper that I found. So that is what we'll go into. It comes up with, there are three key contributions. One is a structured and generic thought template library containing around 500 high-level thought templates capable of generalizing to similar or relevant reasoning problems. So these are your Lego blocks. Now, what are those thought templates? What do they look like? We'll see shortly. Performing hierarchical reinforcement learning on a sequence of thought templates instead of original long COT data. Optimizing a base LLM plan to plan out an optimal trajectory for gradual handling complex statement. A very long statement. Basically, what it means is that you don't use reinforcement learning with COT data. You use a very different method for reinforcement learning, this hierarchical reinforcement learning, where you work with a sequence of thoughts rather, thought templates rather. And the third contribution it brings is a brand new inference scaling system that enables hierarchical LLM reasoning by, and this is the crucial word, by adaptively scaling thought templates at inference time. So that in simple term means that the thought templates get modified at inference time dynamically, more items added as needed, as opposed to a fixed budget, and complex problems then naturally end up getting a lot more templates and therefore a lot more computes naturally. So that is this paper. Now, I suppose this paper starts out with a performance benchmark to illustrate the point that it works quite well, this benchmark. So this column, if you look at it, now something to observe about this column, look at V3. A DeepSeek V3 is, if I remember right, a 671 billion parameter model. OpenAI's O1 preview, it is undisclosed how big it is, but one would assume it is in the same order. O1 mini is maybe perhaps smaller, but also a huge model. Then GPT-4-turbo is also a huge model. QWQ is the only model of comparable size, QWQ. So if you look at this, you observe that on math, it beats all of them, though it beats DeepSeek and QWQ by a slightly smaller margin, but still a valuable margin. Likewise, in all the benchmark, it does achieve the state of the art. Now, what is this? What is the key idea? What they say is this whole dynamic thinking is that when we try to solve a problem, we all start solving a problem. And as the results come, you solve a math problem, you figure out some things. And based on the outcome of that, it gives you more ideas and you evolve your approach to solving the problem. And that is the gist of what they're going to do. They're going to evolve their thinking process as at inference time. Remarkable idea. So let's, I'll study this paper through its key figures. So first is, how does the training happen and how does the inference happen? It turns out that it uses two different forms of training. One is supervised fine-tuning and one is reinforcement learning, and we'll come to both. But this picture is interesting. Given an input problem, ReasonFlux will now dip into its thought template library and pull the most relevant thoughts. For that, how does it know which is the most relevant thoughts to pull? That is the supervised fine-tuning part, But let us assume that it does manage to get those thoughts in the system. And once it gets those thoughts, so this is here, those thoughts are here. And then what it does is it creates a trajectory. It will say, to solve this, I need to do step 1, step 2, step 3, right? Then it could come up with an alternate trajectory. It may say that to do this, perhaps I need T1, T2, T3, T4 as steps, and so on and so forth. So you can end up with multiple trajectories with each with different number of steps. And now what you do at training time is that you create a reward model. We will see how it does that. It's a very straightforward way. You see, if you follow each of the trajectory, how good is the output? In math, it's quite obvious. Did it lead to the correct answer? Right? And so you can score, you can associate a goodness score to each of the trajectories, I suppose using some form of partial scoring or something. Then you can use that trajectory, and this is where reinforcement learning comes in. Once you can associate a reward to each of the trajectories followed, then it opens up the possibility of reinforcement learning. In other words, you train this model, ReasonFlux, to pick the best trajectory. And once you have the best trajectory, it is used then to solve the problems. That's the basic idea of this paper. So I'll read the highlighted parts. It is talking about prior research. What is the approach that other people have used so far, and what are the limitations of those approach? So it talks about, it's highlighted here, but I'll just summarize it in my notes as 3 key approaches. One is deliberate search, chain of thought, tree of thought, graph of thought, and obviously increasing compute costs. We are all, I suppose, hopefully familiar with. These are step-by-step process of solving a problem. Break it down to smaller pieces. Chain of thought is straightforward. It's a way you would solve it. Tree of thought takes a more tentative approach. It takes a step and says, now what are the possible steps I can take? And then explores down those and keeps the more promising steps and prunes out the less promising ones. That's a tree of thought. And the graph of thought just generalizes it to a graph, because a tree is a graph, but it allows for sharing of good steps between different approaches. So that is the deliberate search. And it has been, of course, around. If you notice, models are being heavily trained using one of these approaches these days for reasoning. The other sort of methods that have existed for a while are reward model guided methods. Right? And what do those methods do? Those methods to assess the reasoning step quality. Now, for example, best of n approach. So you use something called output reward model. It's a word that is there in this, it's part of the vocabulary here. So you generate multiple candidates, n candidates, and then you say which of these were the best. You give a output reward based on whichever led to. Then there's another alternative. These are called process reward models. They guides towards promising paths through rewards. So it just says that, oh, that step looks better. Here's a reward for that, greater reward for that, more promising step as you solve this thing. And obviously, one of the things that has been very popular is the Monte Carlo tree search. For example, the game of Go through the machine, and that AlphaGo was trained to beat using the Monte Carlo tree search. It breaks down to simple steps and uses process reward model to guide actions. Action selection in a tree search space. So you have a tree, you have multiple paths you can take in the tree, and which particular path you take is through a process reward model. So that is the second approach, reward model based. And the third approach that is also popular is RAG-like approach. So what you do is, as the machine solves different problems, it creates a buffer of thoughts, buffer of good thoughts. And those buffer of good thoughts become its repository into which it can retrieve and search for good thoughts or the most relevant thoughts appropriate to solving this problem or germane to solving this problem. So those are RAG-like approach, and buffer of thoughts is, I suppose, a popular candidate for those approach. For each of these approaches, as you can imagine, RAG problem is it doesn't scale efficiently because you can end up with a huge sort of a index or a repository of lots and lots of thoughts, most of which may not be relevant to your problem. Right? And so it doesn't scale that well. So having set up these three approaches, which are prior efforts, we now go to what they have to provide. Right? So what they say is that essentially all of the prior approaches, they struggle to effectively balance the exploration exploitation trade-off during inference scaling, which is the thing. See, at any given moment, the point is, if your solution space is vast, you have one thing you could do. You could go exploring throughout the feature space, looking for solution, and spend a lot of compute budget there. Or you take the first promising idea that comes, that you stumble upon, and you start exploiting that. But it may not be the optimal one. So this has always been a sort of a dilemma, and you have to keep some budget for exploration, some for exploitation. And that is it. And that is where you need more efficient and generalizable inference scaling approaches that enhance reasoning without extensive manual effort while providing a more principled search strategy. So that is the core value proposition of this paper. So now let us go through what they are talking about. To this end, we introduce ReasonFlux, a novel hierarchical LLM reasoning framework that configures optimal thought template trajectories by automatically retrieving relevant high-level thought templates at inference time to achieve superior performance on complex reasoning tasks and even outperform OpenAI's O1 preview and O1 mini model. So let's unpack it. What they're saying is, let's have a library of 500, in this particular case, 500 odd thought templates. They are like Lego blocks. And you have curated this collection of good Lego pieces. That is one thing you have to do. You have to create these Lego pieces. How do you create these Lego pieces? What they did is, they took standard math problems from standard data sets, and they looked at the solution. Then they gave it to Gemini 2.0, and said that given this problem, given the solution, now abstract out or create something called a thought template, or the core approach that is used to solving it. So you work backwards. You're saying, here's the problem, here's the solution. We know that is in the benchmark data, but now take the solution and abstract out the approach from the solution. Right? So that it is generalizable. You can generalize to other similar situations. And that is a key insight. They do that. So they say we first construct a structured template library which contains 500 useful compacted thought templates. They keep emphasizing the word 500 compacted thought templates. Because searching through 500 is easy, isn't it? And given a problem statement, given a thing, to determine which one to use is in a way a classification problem. Here's a sub-problem. I need to, let's say that I get square root of 1 minus x square, right? So if there is a thought template that says, hey, why don't you make x into sine theta? Then it will become 1 minus sine square theta, and that will be cosine square theta, and square root will be cosine theta. So there is a thought there. And basically, a machine has to determine for this step, which is the best thought to pick. It becomes, in a way, a supervised learning problem and a sort of classifier problem for this step, which is the most appropriate template to pull forward. That is what they are saying. That's why they emphasize that having a small library makes a huge difference because you're predicting into it. And they say instead of optimizing a long chain of thought trajectory, we perform hierarchical reinforcement learning, etc. So some of these things that they claim, the meaning becomes clear as we move through the paper. But we'll figure it out. And so what I thought at this moment I'll do is I will just lay out the approach that they use in a very in a sort of an intuitive manner. Okay, let's look at these equations. It's best understood in terms of the equation. So I'll forget about the general discussion. First step is construct a structured thought library template. So you create a library of good templates. Right? Here's an example template that they give, and the appendix gives you a longer template. So suppose you're solving a math problem like the one here. Let's look at this math problem. Now, this problem, if you are still, you recall your trigonometry, this is almost a giveaway. You would say, okay, if I have r squared minus x squared, the easiest way to solve this is r sine theta, something like that. Right? If x is equal to r sine theta or cosine theta, it doesn't matter. And so this will become r squared minus r squared sine squared theta, and that will become r squared 1 minus sine squared theta, which is r squared and r squared cosine squared theta, and that is r cosine theta. Right? So what you can do, therefore, is this is an approach to solving a problem of this type. If you get a math problem where you notice an expression like this, you can say, okay, I have a trigonometric substitution as a thought template. It's an approach. Think of it as a mathematical trick to solve this particular thing. And so that becomes one thought template, which you give it a name. Right? The whole name is, you even give the mathematical expression, and then you give a tag, substitution method, trigonometric substitution, irrational function. Tags, why? They're good for keyword search. And then you give the description. And here is something interesting. You give it the description, and the description goes on and on. Then comes a very interesting thought. What you do in this first part is the structured fine-tuning. What does this structured fine-tuning do? It says, if you look carefully at the last function, which looks complicated, but I'll just explain. What it says is, you take a machine which you have trained with this. If you give it the name of a template, the tag of a template as input, right? Template name, template tag as input, can the machine predict, or in a way generate the actual content description, or and etc. Description, the scope where it is applicable, and so forth. So simply put, given just the name and tag, very basic information, can a machine therefore, could it have learned that this tag means generate this description, the complete details, right? And you do that with supervised fine-tuning. That's why you have this equation that what is pi? You have a model whose job is, pi is the probability, of predicting that particular detail. I'll just write it as detail from just name tag. Right? Given name tag, come up with a thing. And if you want to make sure that the right detail has the highest probability, of course, this is your standard negative log likelihood function. So you would do an expectation value, sampling from the D train, like whatever training data sets you have, of the log of this. So this becomes your standard negative log likelihood loss that you do for a classifier training, right? Or for this situation, or this generative thing to generate the details of it. So this should be, I guess, I'm just mentioning it in case you're wondering where this comes from. In other words, if the probability of the right details is low, it means the machine still has to learn something. Right? That is the loss. And that is what it is when they say that this is where the objective is to maximize the likelihood of the model generating the correct description and scope, basically the details, given the template name and tag. So now let's step back and ask, what has this approach achieved? What this approach has achieved is that this particular model now, whichever model you train with this SFT, will understand inherently all of those approaches, those 500 approaches, because it will be able to, in effect, regurgitate those approaches simply from the name and tag, isn't it? It's almost like you say tale of two cities. And immediately the machine starts saying it was the best of times, it was the worst of times, and so on and so forth. Right? Starts quoting the book. So pretty much that's the intuition behind it. But once you have done that, now comes the interesting thing. How does this approach really work? The way it works is, so imagine that you are given a problem X. There is a planning phase. This machine will do this. It will come up with, it will say, to solve this, I need to do steps S1, S2, Sn, right? In this order. I need to do these steps to solve it. Now what will happen is, this is a trajectory. This is a particular trajectory of steps that it can take to solve it. Now we don't know whether it will actually solve it or not, but it can break it down to this step. So that's the planning thing. You let the LLM, you let the model say, okay, if you want to solve this, it makes sense that we should break the problem down to these steps. Then question is, how do we do these steps? Aha, I already know, given a step, what is the best thought template to pull forward, right? So now I can go and bring the thought template T1 or T2, the appropriate thought template can be brought in, right? And then what you can do is, then comes an interesting thought. You take another model. So remember this model that you're training, this is called the pi struct. Let me call this pi. The first model is struct. What was the job of the pi struct? The first job was to predict or to know, given a step, which is the best template to pull forward, right? It knows it because it has memorized the description of those templates. It pulls those forward. Now comes the reinforcement learning part of it. What you do is, you say this, you take another model, and this is the part, this is the model that will go through SFT and reinforcement learning in a bit, training. So think of two models, model 1 and model 2. And very concretely, what they did is they just took Quen, 32 billion parameter model, right? Which is a Quen 2, I believe, a 2 something, a 32 billion parameter model. 32 billion parameter models today would be considered a baby model, right? You take a small model, one copy of the model you put through this exercise. Another copy of the same model, you just leave it alone. You just call it pi inference. You don't touch it. One reason to derive of the same base model is there won't be compatibility issues. You're just working with the same base, right? But to the inference, what you say is, here is a step that you need to do. Here is a step. Here is a thought template that is most appropriate. Here is a thought template. Here is this, and create a go solve it. Instantiate. They call it instantiate a solution. The partial solution from it. And so what will happen is, For each step, there will be a thought template, and SI, a thought template TI, will lead to some result. The output they call SI, they put a hat on it. They say that this model will produce some output. It will say, okay, I substituted cosine theta here. And because I substituted cosine theta, this is the result. So now what will happen is all of this S1 hat, S2 hat, the way machine will go about solving the problem, Sn hat, and this will be one trajectory. It will be a trend. Now you have to do one thing. You have to, especially if it's a reasoning or math problem, you can always look at the solution and tell how good the solution is, isn't it? You can say that, well, does it work or not? And that is what they do. But they do something more interesting. Instead of giving it a score just to that particular solution, they do a little bit better. For a given input, they create multiple variants of the input, similar variants of the input, and they pass it all through the same trajectory. And then the accuracy of that approach, not only of that, just to make sure that it wasn't an accidental hit on the solution, it was really reasoning properly, you take an average of the accuracy. Right? So for example, if you're doing 3 plus 5, then you can say 4 plus 6. Or something like that, similar addition problems, and you see how well this model does. Then use that to, now it is easy. A reward function is literally, for example, what a teacher gives when a student does a quiz, right? A score. You can take the average score, and that is it. Once you have done that, now what has happened is you had multiple trajectories, like this machine was asked to, at training time, create multiple trajectory paths. If you look at it during training, here we go. It has created a trajectory 1, trajectory 2, trajectory 3. Each of the trajectory will therefore have different rewards. You can take any pair of trajectories. One will have a greater reward than the other, isn't it? One will be slightly better than the other. So what you do at that particular moment is you bring in reinforcement learning, and in particular, you use this formula. If you look at it, this is basically your direct preference optimization. This is a reinforcement training through direct preference optimization. Now, this function, if you have never seen, let me just give you an intuition of this function. It's not as scary as it looks, actually. What this function is trying to say is, leave your model, the SFT model. So let's look at that. You took a model, base model. From that, you did SFT, and now you're doing RL, isn't it? This step, equation 4, is the process of doing reinforcement learning. So you leave your SFT model as a baseline. Now, what would you like to have? You would like to see that your good model produces a trajectory, prefers a good model should prefer a good trajectory rather than a lousy trajectory. Right? A good model will always lean towards picking a smarter approach. A smarter approach is a trajectory. Yeah? It should preferably take a smarter approach. So it should, this ratio gives you how much smarter is your model compared to the base model. So the higher the number, the better. Right? On the other hand, you want the probability of probability of the machine selecting a not so good trajectory should be as low as possible. Right? In fact, its ratio to the baseline model should be ideally you want it to be you want it to shrink towards 0 if you could. Right? And therefore, that is why you see this sort of an expression. This is a classic DPO signature, direct preference optimization approaches signature. And so this is it. This is it. So now what happens? Let us summarize what you have done in this process. Let's go through it. What you do is the machine initially comes up with, let's say that you have done this. Now your machine is fully trained. After reinforcement learning, the end result you expect is this particular model will preferentially pick good trajectories, isn't it? It will do good planning, and then the steps that it will pick, the trajectory of steps that it will pick will be the best approaches if well trained. And that is the outcome they are searching for. These researchers are searching for. With that, they say that, well, that is it. And then you have this thing solved, because let's say that you're given an input problem X. First thing the model will do, which is the ReasonFlux. So remember, they use two models here. So Pi went through, the initial model went through Pi SFT. Pi SFT went also to SFT plus RL. Now RL also came in through the DPO. This final model, they give it the name ReasonFlux, and they keep another copy of this model as the inference model, a simpler model. They just leave it alone, no supervised fine-tuning, no this. And what they are doing is that the job of the ReasonFlux is to actually do the hard part, break up a problem into smaller parts, smaller steps, figure out the right templates, right? And then give it to the inference model, inference model, and say, hey, okay, here is a step and do it using this template. This is sort of like your in-context learning kind of a thing. Do that. And then the inference model will say, okay, I'm going to now start using this example to solve this problem, this demonstration to solve this step. Right? And it will do that. So it's an interplay between ReasonFlux model and inf model. There are two models. There's a continuous interplay between these models. So let's look through the steps, and this is important. Now we go into inference mode. We have trained these models. How does it work? Given an input problem X, the first task for ReasonFlux is to analyze and extract the core mathematical concepts and relationship within X. So that is essentially based on this abstract denoted as X. So it comes up with a mathematical understanding of it. ReasonFlux then configures the optimal trajectory. So now it has been trained to find a really smart trajectory of steps. It will become steps. What do we do with those steps? So these steps will become, again, templates, as I've written it down here. Templates. Those templates will be name tag. Now the machine is very clever. It knows what the meaning of those templates are, right? It can then generate the text, the descriptions associated with it, and then give it to the inference model to generate the data, to the actual instantiated steps. Did this, did this, did this. Now, here comes the fun part. So here we go. This is the result of, this is the result of the ReasonFlux. It has produced a good trajectory, right? This one now goes through this inference model, which is given the input, well, of course, but more importantly, given the step and the template, and it will do something. It will instantiate. It will actually do the compute, step of compute. And then what happens is, while it is doing it, the ReasonFlux model is watching it and seeing the output. It may say, oh, I initially suggested S1, S2, S3, but now not S3, but S4 is more appropriate. S5 is more appropriate. So in other words, based on the actual values that are coming out, it may change its mind and it may navigate. It may change its trajectory. Do you see that, right? Because this model, the ReasonFlux part, through reinforcement, it is observing the trajectory, the output of that trajectory. And it may realize that, there are more subtleties here. Let's change direction a little bit. And so that is what it is doing. So does it actually work? So the first thing is that, and after all this discussion, any questions, guys? I hope this explanation was was it clear? Okay. So then, now it has become common knowledge that to do reinforcement learning these days, you don't need to requisition a hyperscaler's entire farm, cluster farm, right? So you don't have to start with 100,000 GPUs anymore. And in particular, you can see that they start with 8 NVIDIA A100s. By the way, if you go to typical If you go to NVIDIA and say, hey, give me a AI box, AI inference server, it will typically contain 8 GPUs. A100 is beginning to show its age. It's a pretty old GPU. And nevertheless, that is enough. Just using 8 NVIDIA GPUs, which means using just one server, they were able to, in a very cost-effective way, they were able to train this entire thing. And when you look at the results, obviously the results are very remarkable. In this particular table is worth looking at. But before I come to the benchmark, let's see a demonstration of how it actually works. So guys, look at this problem, and I would rather that we spend a couple of minutes absorbing the problem. I will highlight the problem I'll highlight the problem in yellow so that we can all study it for a bit. I hope you realize that this is not an easy problem. So first thing, let us see how alternate approaches, the other state-of-the-art models would do. Here is how O1 Mini goes about doing it. It says, step 1, look for symmetry of patterns. Procedure. Equation seems symmetric in cyclic manner. Maybe there's a relationship or pattern that can help simplify them further. Let's denote A, B, C. So far, so good. Then it says, assume variables are equal. Sometimes assuming variables are equal can simplify the problem. Let's assume X is equal to Y is equal to Z. Right away, it made a mistake. Right? Because you cannot, then the equation simplifies to this. Therefore, our assumption is that this is incorrect. Very good so far. Then it goes on to other things, expression variables in terms of one another. And then what happens is that it goes on thinking. Do you notice that the crucial thing is look at the dot, dot, dot. Right? It goes on thinking and thinking and thinking. And at the end of it, this is its way of saying I give up. This doesn't seem I should consider numerical methods and look for specific values that satisfy the equation. Right? In plain and simple terms, I give up. Right? Now, let's see how this machine, this particular model, ReasonFlux does it. The key to solving it is to determine the conditions for existence of 4 distinct this. So this is its planning. It goes through. I won't read the whole of it. It comes up with a plan. But at the end of it, what it does is it breaks it down into steps. And it says that I need to figure out by analyzing 1, 2, 3, by analyzing positional relationship between, we need to determine the range of values of K. So let's do that. It goes and finds a template. Preliminarily determine the range of K. Analyze the vertices of the parabola and determine the conditions for the existence of intersection points. So it has figured out that it's looking at a parabola. So how does it know that? By the way, if you want to convince yourself, take any one of the equations, square it, and you'll see that you're looking at a parabolic equation, quadratic equation. Right? So here we go. It says instantiate. Since all of them are real numbers, we can be sure that this is true. 2 minus x, etc. are true. Therefore, how do we conclude that that is true? Because of this. If you look at any term, it cannot be negative. If 2 minus x is negative, then the square roots will start becoming negative, right? And you can't have a negative square root. So, square root of negative numbers. So it has concluded this. So it has concluded that the value is between 0 and 2. So far, so good. Then it says, okay, maybe we need a trigonometric substitution, right? You can write any one of them as in this form. So it matches a form like this. And so let us do that. Let us instantiate. It uses this template to, and look at this. It is pretty smart that this template can be used to solve it like this. Let X is, it still needs some thinking to be able to make this step, but this much of step it does succeed in making. And so now it comes up with alternate variables, alpha, beta, gamma, between 0 and pi. And then it goes on and on. It pulls out a third template in the trajectory. So you can see that it is pulling up the right templates. And then it goes and solves this. And then it says that if this is true, then from this we can conclude that these are the only possible values, right? Alpha plus beta has to be pi over 6 or 5 pi. I mean, for example, sine 30 degrees is half. Right? So you do that, and therefore these are the values. You substitute it back. Therefore, you can compute this by substituting back. And so it does that. And so it comes to the fraction 1 over 32. When it comes to the fraction 1 over 32, it concludes that m numerator plus denominator would be 33. And so it solves the problem. If you just look at it, isn't it absolutely amazing that in 2025, the year has just begun and the machines are able to solve what really takes a pretty smart high schooler to solve. And it is able to solve it. Therefore, it's a resounding validation of the approach that this paper suggests. Right? So with that in place, of course, we can go back and look at the benchmarks, and the benchmarks won't surprise us. It is an approach that works. So there are the frontier models of whose details you don't know, and they are open source models. So there are comparisons to both. Look at the math score comparison. GPT-4-turbo, which is a massive model, a really massive model. Nevertheless, it is still at 76. O1 preview is at 85.5, and O1 preview was supposed to be the epitome of reasoning till only very recently. In fact, it's barely come out. And yet you notice that ReasonFlux, at a tiny little ReasonFlux model at 32 billion parameters, is beating it. And it also beats all the open source models also. All of them, it is beating quite well at math and the different benchmarks. So if you saw that demonstration, that example of how it went about solving that complicated algebraic problem, it is no surprise that it is doing so well, because it was clear that O1 Mini wasn't even beginning to think in the right direction. And so one of the questions they ask is, if you do apples to apples comparison, what would happen? If you only took 32 billion parameter models, what would happen? And once again, if you compare with all the known 32 billion parameter models, here, you notice that it beats all of them. Right? Likewise, if you take 7 billion parameter model, you can do that and it will beat all of them. Now, one thing that this paper asks is that they happen to pick Quen as the base. Is it generalizable to other models? Could they have started out by picking any other model? And they do a lot of studies, and they find that yes, it's true. Baselines. You could have taken any good model, any recent model. So the magic is not in the model you start up with. The magic is in the approach. Therefore, it validates that this approach is worth considering seriously, this ReasonFlux approach. In other words, maintain a library of good thoughts, Lego blocks. Whenever you get a problem, decompose the problem into steps. Ask for each step, what is a good exemplar? What's a good demonstration? What's a good thought or Lego block that I can retrieve? Retrieve that, now give it to another LLM and just say, okay, if this is a good demonstration, if this, and this is the step you need to do, go do it, right? And you can build up a solution like that. So that is the main point. And this is the point they say, generalizing to different base models. Right? And we also observe that you achieve. So they try it with many, many different things. And they say, you take all of these popular open source models, and for each of them, you notice that without the approach, without the ReasonFlux, these are but look at the lifts you get when you apply this. The performance lifts are amazing. Right? They're pretty significant performance lifts. Right? The other thing is, does this library only solve the problems it has been trained on or very similar to them, or does it generalize better? So they go on to show that it generalizes quite well actually to different kinds of math problems. Then here comes a very interesting section now. It is the inference scaling laws for template augmented reasoning. So they call this template augmented reasoning. Right? Look at this. What happens is, as you increase, so level 1, level 2, let me explain the x-axis. Level 1, level 2, level 3, level 4, level 5 is the problems that you are throwing at it, they have been categorized at difficulty levels. Level 1s are easy, level 2 is not so easy, and level 5s are absolutely hard. And what you notice is that, and the inference time scaling just means that automatically the machine decides that it needs so many rounds. What is the rounds? It is the interplay between the strategic one, the reason flux model, and the inf model. Right? The reinforce. They keep talking, right? The flux model will give this step and a template and say, okay, now you go instantiate this and make some progress. Then it will go observe, what have you done? Right? So there is a back and forth going on. And so what happens is that this machine, this model is very well able to infer how many rounds it has to go through and how many templates it will use, sorry. And the more complicated you make the model, the more templates it starts using. And it scales very nicely. You see, the inference time scaling is literally with the level of difficulty of the problem, which it reduces very, very well. Now, that is a big positive, because quite a few approaches before this, they would say, okay, I will give this much compute budget to this problem. Right? That budget may be an overkill. And if you remember, sometimes you don't want to ask a simple question, what's the capital of California, to a reasoning model, because the reasoning model goes into a deep philosophical exploration. It might go into, because it has been given too big a budget. Right? Or you don't want to give too small a budget either. The problem exceeds. So it's a problem. You can't a priori determine how much compute budget to give to a problem. And what this approach says is you don't have to. It will automatically scale the compute budget based on the complexity of the problem. Inference time compute. That's the inference time scaling. And the other thing is how well it explores and exploits. The exploration-exploitation trade-off, it does very well. Especially if you look at this particular combination, it is doing very, very few steps, like round trips or steps, and it solves a problem compared to if you use other approaches like Monte Carlo tree search or best of n, which are much more inefficient, right? So because those are the prior work, better explore. So that is it. And that is the gist of it. If you want to see what any template looks like, it's a pretty detailed template. Problem solving, 5-step method for solving absolute value inequalities, for example. So how did they do that? What they did is they took, as I said, they took a problem and its solution from some benchmark database, and they gave it to Gemini 2.0 and say, okay, I noticed there are some questions that are there. Oh, everyone jump to the Fuji course. Oh, I'm not able to read. Somehow it's coming out in very big fonts. So I'll push back now. And are there any questions, guys?
I can ask a question.
Yes.
I'm noticing it's mainly mathematical examples. Oh.
Oh. Yeah.
Wow. Okay. Yeah, I'm noticing it's mainly mathematical examples where they can create these templates. Do you think it generalizes in some way to non-mathematical examples, maybe other domains? Like it seems like programming would be a great.
Yes. See, one thing we are finding, or people are beginning to believe, that a machine, a model that can deal with mathematical reasoning, generally, mathematics is applied reasoning, applied logic, and so is programming. Right. So obviously, this paper has limited itself at this moment to math related, but to the extent that both math and programming are applied logic, it is generalizable, one would imagine, to that, because that is the common belief these days, that train a machine to do really well with math. If it can do the math well, it can do other things also well using that approach. But one would imagine that directly, I don't think that this can be applied to coding. You'll have to create the template library. Remember, thought template library for that, right? And whether it's even needed, see, programming is orders of magnitude easier than solving math problems, right? Especially math problems of this complexity, level 5 complexity. So, so that is that. That is one limitation of this paper, which is that you better have a really good curated collection of or library of templates, thought templates, because it is leaning heavily on that.
So Asif,
Yes.
this is another way of fine-tuning the model. So I have to set 500 templates. I can fine-tune it for my problem, for any problem.
Yes.
If I build them.
Yes, yes.
So I don't have to follow the other fine-tuning methods.
No, see, it is a combination of two fine-tuning techniques, a supervised fine-tuning, just to train the machine into the details, generating the details, so that what you are actually saving or predicting, saving are just the template name, etc. But that's a technicality, a detail. But more specifically, you're using reinforcement learning to be able to weave together the perfect trajectory of steps. That is the magic. That is still reinforcement learning. And they use a direct preference optimization like approach to do that. So here's the thing. Most of the time, so just to give you a contrast, most of the time machines are trained to predict the better token, next token. But do you notice that it is not thinking in the level of next token? It's taking a pretty hierarchical approach. It is saying break it down into steps, from the steps then instantiate it, and come up with the best trajectory. And then for each piece of the trajectory, determine the best template. And once you have done that, the game is on. A simple model can therefore solve that step, and the collection of all those small solutions is the full solution. That's what this paper is saying. All right, guys. Any other question? I don't know if you guys have this paper.
Yeah, go ahead. Shirang here. Two fine-tuning techniques you mentioned. We got the thought templates. So what was the other one?
Supervised fine-tuning. So let me go back. See, this is it. Just from the name and tag, generate the description. That is it. That's the first part, right? The machine is trained to understand exactly which. If I pull those templates just by name, I can tell.
Right.
Then there is a reward function, which is just averaging over how well it solves a problem and similar problems. And then there's a DPO like reinforcement learning is in this equation. This is it. It's a set of these three ideas.
Got it.
Yeah. And I felt that this was really well done, very, very well thought out. And I don't know what subsequent work will come, but it's neat. It's neat that it can do it so well.
So just to push this a little further, we could basically set up a very simple problem without going into massive details and say that, hey, there are only, let's just say there are 2 or 3 templates we have, and create a problem which just chooses one of, essentially it consists of choosing one of the 3 templates or so. So technically we could also train the model, a simpler model to do this.
That's right. See, you can do that. You can work with, and they do that, right? They go down to 1.5 billion parameter models that they have trained. Now, see, the problem that happens is, even if you have a library of, let me just say 10 templates, trajectory is a bit of a hard problem, because you realize that, suppose you create first you don't know the length of the trajectory. Can I solve it in 1 step, 2 step, 3 step, 5, 6 step? Let us say that hypothetically, you can solve it in 10 steps or 5 steps, just to pick a number. You realize that you're looking at how many possible trajectories are there, 10 to the power 5. Even with such a small library, there are 10 to the power 5 trajectories possible, even if you insist on a 5-step solution, which may not be enough there. And so 10 to the power 5 is a pretty large number, 10,000, right? And 100,000, right? 100,000. So there are 100,000 possible trajectories. And that is where reinforcement learning, this equation 4, helps you. The machine learn to zoom into the right trajectory. That will help solve the problem. But when you scale to this problem, 500, let's say that it solves. So think about it this way. Let's go to the demonstration they gave. Look at this. So how many templates are there? 1, 2, 3, 4, and then there's a final step. Let's say 5. You realize that each time, even if you take 4, each time it's picking a template out of 500. Right? There were 500 possibilities. You're looking at 500 to the power 4. Right? 500 is half of 1,000. 10 to the power 3 times 10 to the power 4. That's 10 to the power 12 divided by approximately half. So let's say 16. So basically, let's say 10 to the power 11. You're looking at, what is it, 100 billion trajectories possible. Out of the 100 billion trajectories possible, the reinforcement learning has guided it to pick the optimal trajectory. Just think about it, like what an amazing feat it is.
Yes, indeed. What is sort of behooving me to chase something like this is physical problems solving. Let's just say getting from one place to the other, or solving any enterprise-related problem. When it comes down, when a query comes, how do we break it down to follow a thought process? It very much seems like this is the technique to follow, because every enterprise software or any particular data wrangling or whatever needs to happen, it follows a particular pattern. There are not a whole bunch of crazy patterns that a particular software or deals with.
Yes,
So
you can break it up. You can break it up, because most code, after a little while, at the basic level, follows some very common idioms. And so if you can templatize that, you could do this. I mean, see, that's the whole point. Any given domain, there are only those many tricks or those many operators that you can have. If you can templatize all of them, then one would imagine that this approach is generalizable to that.
Right. So my idea was that once a query comes, you break it down into the steps, and then based on the steps, you align your agents, saying, hey, now the first thing is to break it down. And once you break it down, it's like the orchestrator agent. And after that, the first one says, oh, go to the database, get this stuff. That's first thought template. And after that, go do this. So essentially, then lean on the other agents to do the, per agent.
Easily possible. What you are saying, if you are trying to extend this to agentic reasoning, what you are creating is a trajectory of tools or trajectory of agents, whichever way you want to look at it, agents capable with certain abilities. You can reason through that you have to just take a problem and decompose it into a trajectory of.
Right. So I tell you a standard problem that happens in architectural construction. So there are issues coming, there are RFIs coming, and ultimately they are trying to find out, based on relationships, whether there will be an impact to a schedule. Schedule is getting impacted. So if you can break it down, the question and the issues coming in, and relate it to schedule somehow, then the problem is solved. And this, because everybody wants to know what is the impact of the schedule. So
Yeah, I would
not as
imagine.
you go ahead.
No, I would imagine so. This paper limits itself to this. I mean, see, good papers open the door to new work. And so, like you are bringing up these possibilities, I think those possibilities are certainly promising in view of this paper, and they need to be investigated.
Fantastic. Thank you.
Anybody else, guys, any thoughts before we conclude? All right, guys, I'm going to end this thing if there are no other questions. I hope you enjoyed it. It was a technical paper, quite involved, but I hope you got something out of it. Bye, guys. Good night.